This third part of Chapter 16, now we're going to talk about capacitors, because capacitors store electric energy. So what is a capacitor? A capacitor does store energy in the electric field. So what we see in this diagram is electric field lines. And we basically have one plate that is positively charged and one plate that is negatively charged, where we have forced these electrons on by creating a potential difference and forced the electrons to come from the battery and onto this plate. And in that process, the excess electrons from this conductor are removed and go back to the battery. So we force the electrons on, which basically chases away the electrons from the other side, since they are capable of leaving. So one plate ends up being positively charged, the other plate is negatively charged. And that's exactly what we have here. This is called an air-filled variable capacitor. So again, great naming. It tells us exactly what it is. It's air-filled because there's air between the plates. And it's a variable capacitor because this is a knob that we can turn. But I like this capacitor, and I have a few that I can show off in class that you really see the parallel plates. That's exactly what it is. And so it's variable because as you turn these, sometimes they're overlapping and sometimes they are not. But you can actually see that there's variable plates. Now capacitors come in all shapes and sizes. So here you see a couple of these air-filled capacitors. But you have these ceramic capacitors, you have these barrel capacitors. There's capacitors come in all sorts of shapes and sizes depending on what the technology is inside those capacitors. So what is a capacitor? What are the equations? Well, this is what we call the capacitor equation, and that's from that if we have an electric field, the electric field is directly proportional to the amount of charge that we have on there. That should make sense. The more charge we have, the more electric field that we're going to have. And the more charge, the more voltage we're going to have. And so therefore we can say that Q is directly proportional to V. And as we do a lot of times in science, we need a constant of proportionality. That constant of proportionality is what we're going to call C is our capacitance. So what is this capacitance? Well, we know that delta V is equal to E times D. That's one of our fundamental equations. And the electric field is equal to sigma over E naught. That was from Gauss's law. And we know the charge density, sigma, is Q over A. And so therefore the charge, if we rearrange this equation, is equal to E naught A over D. And so therefore this is what we're going to call our capacitance. And here I've given it a subscript naught because this is our base capacitance for a capacitor filled with air. We're going to talk about if we fill it with other materials, but that is our capacitance if our dielectric is air. And so it depends only on the area and the distance between the plates. So that means if our area increases, then C increases. But to get C to increase by the distance, we want to get this down. So that means a really, really good capacitor is going to be really, really big area and the plates really, really close to each other so that those charges can get close but not touch. So that's what we want for an ideal capacitor. So these are typically pretty small devices because the distances are so small. So the capacitance depends only on its geometry. And the unit of capacitance is given the unit of a farad, which is a coulomb squared per joule or a coulomb per volt. And so here's some of our capacitor construction where you can see that the air-filled variable capacitor, we have plates that can overlap or not. We can also form these cylinders by wrapping up layers. And so you can see how these distances could be very, very tiny, because you can make a capacitor at home by just taking a sheet of tin foil and a sheet of wax paper and rolling them up together. Okay, so now we get to do some math. A parallel plate capacitor has a capacitance of 1.2 nanofarads, and nano and microfarads are pretty common. In lab, you're going to use a 1 farad capacitor, which is like huge compared to most of the capacitors. And has a charge of 0.8 microcoulombs on each plate. And so the first thing we want to do is figure out what the potential difference is between the plates. So we're going to use our capacitor equation to do that. So Q is equal to C delta V, and I'm going to solve that for delta V is equal to Q over C, and those are the two numbers we're given. This is 0.8 microcoulombs over 1.2 nanofarads. Micro and nano, how do I do that? So micro is times 10 to the negative 6 coulombs, and nano is 10 to the negative 9th farads. So that gives me 667 volts as the voltage. So even though we're dealing with teeny tiny coulombs and farads, large voltage. And then the next question, which is going to be a challenge question for you guys. So this question you're going to have to answer on eLearn is, what if the plate separation is doubled and the charge is kept constant? What will happen to the potential difference? So to do this, we're going to look at the formula delta V is equal to Q over C again. And we know C is equal to this, so we're going to substitute that into the equation. So I get D over E naught times A, and so that means if the plate separation is doubled, so if we double D times 2, then what happens to the potential difference? What happens to that number? Well, it's also doubled because they are both in the numerator. There's all that nicely written out. And then here is another challenge for you. We want to rank the parallel plate capacitors below from the lowest capacitance to the highest capacitance. And I give you the capacitor equation, so pause the video while you give it a try. Okay, so now we're going to go through each one. So the capacitance of A here is A times D. So the capacitance of A is going to be E naught times L squared over A. So we're just going to call that the capacitance of A. Okay, so for the capacitance of B, so here we have basically L squared over A. This one we have E naught is also L squared over, now the distance is twice as much, 2A. So that is going to be quite a bit less. The capacitance of C is E naught. Now we have 2L times L over D, so 2L squared over D. And for this one, we have 2L times 2L, so that's going to be 4L squared over D. And this one is going to be 4L squared over 2D. And we can simplify that, we get then 2L squared over D E naught. So now we need to rank them. Well, this one's going to be the smallest because it's 1/2. This one's going to be 1/2 CA. This one ends up being 2 CA. This one ends up being 4 CA. And this one ends up being 2 times CA. So we have all those related to CA, and obviously this one is CA again. So this one's going to be the smallest. So CB is the smallest because that is 1/2 CA. So that's going to be smaller than CA. And CA is just CA. Then the next biggest one is going to be 2 CA. And so that is going to be 2 CA is both CE and CC is twice CA, and the biggest capacitance is going to be 4 CA, which is CD. So that is our rank order on those guys.